All right, in section 2.7, we are looking at graphing various linear and absolute value inequalities in the coordinate plane, okay? All right, now we have experience graphing inequalities on a number line, and these would be one-dimensional inequalities, okay? So I want to show you how the one-dimensional inequalities relate to two dimensions, okay? Your solution to a two-variable inequality, it's typically an infinite set of ordered pairs that can be represented graphically with a shaded region, right? You can't possibly list out an infinite amount of ordered pairs, so the graph is just a visual to represent your solution set, all right? So over on the left-hand side here, I have a one-dimensional inequality. X is greater than 2, meaning our solution is all real numbers whose values are larger than 2. And we know how to graph this, right? On the number line, let me label here. Just going to put 0 in the middle, make that 2, that -2. And for this particular solution, we'd put an open circle at 2, and we'd put an arrow over to the right, okay? Now, if we want to move from one dimension where there's only one value of x at play and then go into two dimensions, we need to bring a second variable of y into play, okay? So what I'm going to do is I'm going to take x is greater than 2 and I'm going to add in 0y to it. So now that it is can be thought of as 0y plus x is greater than 2. And now I can graph it two-dimensionally in the coordinate plane. Okay, now, basically, whatever happens in this inequality doesn't matter what the value of y is, x is always going to end up being greater than 2. So what we're going to get here is we're going to get a vertical line, which I'm going to represent with a dashed line here. And that would be at x equals 2, okay? And then if I want any point whose x coordinate is greater than 2, and it doesn't matter what the y coordinate is, then that would be any of the points in this region right here, okay? So make comparisons between the one-dimensional representation and the two-dimensional representation. Notice that in 1D I have an open point, and in 2D I have a dashed vertical line, okay? If I had had a solid point, then in one dimension, then in two dimensions, I would have a solid line, okay? The dashed line is telling me that all of the points that fall on that line are not actually part of the solution set. Why? Because their x coordinates are equal to 2, and we want points whose x coordinates are greater than 2, okay? The shaded region represents all of your solutions, though, so those are all of the ordered pairs whose x coordinates are greater than 2, doesn't matter what their y values are. And notice how that just matches the line pointing to the right in the graph in one dimension, okay? So hopefully that helps make a connection between inequalities in one dimension versus two dimensions, okay? All right, now let's get into some linear inequalities here. I would like to graph each of these solution sets to the inequality. The graph is going to represent my answer, okay? So basically, in the case of a linear inequality, you're just going to graph what's going to be referred to as the boundary line first, and then you have to determine after that where the shading should occur, okay? So let's start with y is less than or equal to 2x plus 1. I'm going to graph the line first of y equals 2x plus 1. It has a y-intercept of 1 and a slope up to right 1, where you go down to left 1. Fill up the graph with as many points as you can, and then we're going to connect all those points with a solid line. That's because Notice in the inequality, you have the equal to portion, right? Y is less than or equal to 2x plus 1, which means all of the points that are on this line are part of my solution set. They make the inequality true, okay? Now I just need to determine which side, which region on the left side of the line or on the right side of the line is my solution set. And to do that, I'm going to use a test point, okay? I'm going to pick a test point of the origin, which is usually the point you're going to want to use. The only exception would be if your boundary line goes through the origin, then you got to pick a different point as your test point, okay? Now, what do I mean by test point? Well, I'm simply going to plug 0 in for x and for y in the inequality, and I'm going to see if I get a true statement. 0 is less than or equal to 2 times 0 plus 1. That's going to lead me to 0 is less than or equal to 1. Once you get here, you ask yourself, is that a true statement or a false statement? In this case, it is true. Okay? So that means the origin is a point that's in the solution set. Well, the origin is right here. It's to the right or below the boundary line, depending on how you want to look at it. So that means all of the points that are on that half of the line, they're going to be part of your solution set. So you're going to shade this region to represent that solution set. Okay. All right, second example here. Our inequality is in standard form, and I'm gonna keep it in this form. I'll find x and y intercepts. So your x-intercept would be 6. I'm going to have to plot that a little bit off my grid here, no big deal. And then my y-intercept would simply be if I plugged 0 in for x and solved for y, I would get 1. Okay, so there's 2 points to define the line. I'm going to connect them with a dashed line. Okay. The reason I'm using a dashed line is because if you notice the inequality, it doesn't include the equal sign, right? X plus 6y is just less than 6. It's not less than or equal to 6. So the points on this line are not actually part of the solution set. Okay? So now I'm going to pick my test point. I can use the origin again. And plugging 0 in for x as well as for y, you end up with 0 is less than 6, which is another true statement. Since that's true, that's telling me that the origin is part of my solution set. Notice the origin is below my boundary line, so this entire region below is my solution set. Pick any point in that region. If you plug it into the inequality, you'll get a true statement out. Any point that's in the other region that I didn't shade, if I were to plug its coordinates into the inequality, I would get a false statement. Okay. All right, so that's it for this video. I'm going to cover examples 3 and 4 in a second video.